Okay, so we are going to look at Chapter 4, exercise number 14. So Chapter 4, exercise 4.14. This problem reads, a supply plane needs to drop a package of food to scientists working on a glacier in Greenland. The plane flies 100 meters above the glacier at a speed of 150 meters per second. How far short of the target should it drop the package? Okay, so if we think about our problem-solving process, we first want to identify the object of interest. That's going to be the package. The package is what is going through the motion. So we want to remind ourselves that we are interested in the package. Now, when we think about what this motion is all about, what starts the motion, what ends the motion. So what is our initial, what begins that motion, and what ends the motion. Okay, so it starts when the package is released, and it ends when it hits the target. So we are interested in the motion of this package flying through the air. So let's think about what type of motion that is. It's flying through the air. That's free fall. And is it moving in 1 and 2 dimensions? 2 dimensions. And it's a single object. So we have one object, 2 dimensions, free fall, projectile motion in this case. So it is always helpful to remind ourselves sort of the parameters of that project. So projectile motion, 2 dimensions, 1 object. All right, next step is to draw a picture. So here's our airplane, here's the ground, here's our scientists down here on the ground. All right, we want to drop that package in enough distance before the scientist so that as it falls through projectile motion, it hits the scientist. So on our picture, we have to define 2 dimensions, 2 origins, 2 of everything. We double our work. So we have to define a position 0, an origin horizontally. So we have a horizontal origin of 0. And we have a vertical origin of 0. So I'm going to define my horizontal origin at the plane in the XY, and I'm going to define my vertical origin at the ground in the Y direction. All right, so those are my origins. Now I can make my list of knowns. So I have both my horizontal list and my vertical list. So I have position horizontal initial, my final position horizontal, my initial velocity horizontal, my final velocity horizontal, my acceleration horizontal, and my time. Right? Then vertically, I have my vertical initial position, my vertical final position, my initial velocity vertical, my final velocity vertical, my acceleration vertical, and again, my time. There's no vertical or horizontal time. Again, as you've learned and as we've discussed, time is for both dimensions at the same time. All right, so what is my initial position horizontally? Well, I set that at the plane's X position, my origin, so it starts out at 0. What is my final position? Well, the problem does not tell us what our final position is. That's what we want to know. And so we're going to keep that in mind. We don't know our final position. It's going to land here at these people. My initial horizontal velocity, it says it's flying at a speed of 150 meters per second. And I think we can make the assumption that that flight is horizontal. So our initial horizontal velocity is 150 meters per second. In 2-dimensional motion, horizontal velocity doesn't change. There's no acceleration. So our final horizontal velocity and our initial are the same. Our acceleration is 0. And we don't know the time. In the vertical direction, it does say that we're flying at 100 meters. So we have our 100 meters to begin with because I've set my origin at the ground, and we end on the ground, so we end at that origin. If we're flying purely horizontally, our initial velocity vertical is 0 meters per second, but it does change. We accelerate in the vertical direction in the case of projectile motion or free fall. So we don't know what our final vertical velocity is. We are in the case of free fall, so acceleration in the vertical direction is that which is due to gravity, so 9.8 meters per second squared. And again, I don't know my time. So here's what we know, what's given to us, what's implied based on what the problem, and what we've defined based on the origins. All right, so now we have to figure out what answers the question. It says, how far in advance of the scientist do we drop that package? So we know we drop the package at 0, that's what we've defined it to be. But how far away is 0 from where those scientists are? That is given in our horizontal final position as I have defined the problem. So x final horizontal is what we're interested in knowing. All right, so now we have to pick our equation. Well, I like to start with the one that has all that fun information. X final is equal to x initial plus v initial t plus 1/2 acceleration times time squared. Now we're going to be looking at that in the horizontal direction along this list. So x final is, we don't know, that's what we want to know. That's partly why we picked this equation. X initial is 0 plus v initial 150. T we don't know, so we keep that as a time, plus 1/2 0 times time squared. All right, so x final, I'm just going to condense this equation, is equal to 150 times time. I need time. I need t to be able to know what my x final position is, so I know how far in advance I need to drop that package. Well, I can't get time from that horizontal list, but I sure can from the vertical list. So now I've become interested in this value. What is my time? Well, I have time in a couple of equations that we use. The one that might make the most sense is what has everything else in it. And again, that's my x final plus x initial. X final equals x initial plus v initial t plus 1/2 acceleration times time squared. So x final is 0. This is my position in the vertical. X initial 100. V initial, well, that's 0 times time plus 1/2 negative 9.8 times my time squared. So now t is the only thing in my relationship, so I can solve for it. And I find that negative 100, bringing the 100 over, this term goes away, equals negative 4.9 t squared, 1/2 of 9.8. And solving for t, I get 4.52 seconds. So now I can put that time back into my equation, and I get x final in the horizontal direction is 150 times 4.52, and that gives me a value of 677 meters. So I need to drop my package 677 meters ahead of the scientists. All right, so quick recap. Identifying what's actually going through the motion we care about, making sure we identify that motion. Drawing a picture so our list makes sense, especially as you're trying to show your understanding of the work. So I'm dropping it ahead of the scientists, therefore my final position is what will give me how far ahead of the scientists I need to do. Going after what we want tells us what we need, then we go after what we need and substitute it back in. Good job.